I'd like to move into one more subject that is unfortunately a bit sad, because sometimes crowd disasters happen. And here are just a few of those examples. The first one shows that the forces in crowds can be so big that they would bend steel barriers. The second one shows that there could be cases where there are hundreds or thousands of people are actually falling like dominoes, as we'll see in a second, okay? Then there could be situations at bottlenecks, such as these emergency exits, where people actually don't manage to get out. So even the policemen don't know what to do about it, right? So there's a clogging effect, and obviously this is extremely dangerous. So these are unfortunately quite typical situations that happen again and again and again. And of course, they should be avoided by better planning, design, and management. So the scientific puzzle really is, why do ground disasters happen? Now, when we started to look into this kind of problem, we were first assuming that people would get nervous. And those nervous people would have a higher fluctuation, higher variability in their behavior. And as you can see, the result is that those efficient lanes of uniform walking direction would break up. And instead, you would find blocks of people confronting each other. And that would, of course, be extremely inefficient and also dangerous, because if those two blocks just are pushing against each other, you can imagine that this could crush people in the worst case. Then we have been looking at bottlenecks, and it turns out that if people are in a hurry, they would push, and that pushy behavior would create a danger of falling, but also it would create a clogging effect. So for some time, people would not flow out of the room efficiently. Now, if instead we are putting an obstacle in the way, this is reducing the pressure on the people at the door. And so the pressure is reduced, and the clogging effect that obstructs the outflow is also reduced. And so surprisingly, the apparent obstacle is improving the flow conditions, right? Crowd disasters happen almost every year until today. And one of the most crowded events in the world every year is the annual pilgrimage in Mecca. Obviously, there are more and more pilgrims every year, so I had to work on the question how to come up with a design that would have a higher capacity and would still meet religious requirements. And from Mecca, then pilgrims move to Mina, which is a few kilometers away. And over there is the so-called Jamrad Bridge. And this is the old design, what you see over here. At this Jamrad Bridge, there have been many crowd disasters. You can see that there's an extreme density around this pillar. There's 3 pillars, actually. So people might actually be crushed, and there could be crowd disasters. And so it was kind of clear that eventually they would have to redesign this, right? So what you see here is Mina. The white area are tents. And over here is the Jamrad Bridge. And the first thing they did is they replaced those circular shapes of the pillars by elliptical shapes that created a larger capacity. And eventually they replaced the old Jamrad Bridge by a new one, which has now, I think, 5 levels. And however, there was another crowd disaster. And that crowd disaster was even in the open area. And so the question is, why did it happen at all? Now, it turns out that this area was recorded by a video camera, and therefore it was possible to investigate this. And it turns out that the flow is actually a merging flow of people coming from two different directions. So effectively, that is really producing a bottleneck, even though the width of those ramps to the Jamra Bridge was 40 meters wide. Because what happened really was that there were unexpected transitions to different patterns of motion. So in the beginning, we had a smooth laminar flow as expected. Then, however, at some point in time, there was an unexpected sudden transition to stop and go waves. And that stop and go pattern actually continued, I believe, for about half an hour, if I remember well. And only after that, a crowd disaster happened. And the crowd disaster happened when there was another transition from stop and go flow to a turbulent flow, which made it very difficult for people to stay on their feet. And so some were falling and others were falling on top. And this is how the crowd disaster actually happened. And this created really important insights. So the first thing is that we were learning about the stop and go waves and why they were actually happening and under what conditions they were happening. And they were basically an advanced warning signal, right? So today we know if stop and go waves occur in crowds, then you need to prepare for action to avoid disaster. Now we do understand the stop and go waves actually. So here is a simulation of the evacuation from a room, assuming pushy pedestrians. So they're kind of trying to get out more quickly than usual. And that is creating a situation where they block each other. So kind of, it's a faster, slower effect. They want to get out faster. The result is it will take more time. These kind of paradoxical effects are quite typical for complex dynamical systems. And this happens because there's a competition for very limited space. So now when looking at trajectories, this is what you find for the laminar phase, the smooth flow. Once you have the stop and go, you'll find the black lines over here, or dots. So stop, go, stop, go, stop. And the blue line occurs when you have actually the crowd turbulence. Crowd turbulence occurs when the density is so high that there are contact forces between the bodies of people. And so forces would be adding up. People would be pushed around in unpredictable ways. And that is what causes the crowd disaster. And actually the way to measure it is not the density, but actually density times variance, which we call crowd pressure. So it's not just the density that matters, it's also the variability of speed. And where this is the highest, where the crowd pressure is the highest, the likelihood of a crowd disaster to happen is high. And this is actually where it did start. And it turns out that the findings that we made are actually also important to understand other crowd disasters. For example, the crowd disasters at the Love Parade in Duisburg, where it also happened that there were these turbulent waves in the crowd, which then later on caused the crowd disaster, okay? In fact, however, it turned out that this was an emergent phenomenon. That means emergent collective pattern of motion that was not desirable. It took many years, and the kind of research that we've done has actually put some light on why this happened, how it happened, how it could actually have been avoided. And it turns out that it was actually a combination of errors that ultimately caused the situation to get out of control. So the crowd disaster over there is basically the result of a systemic failure. That was the area. There's a paper about that if you're interested. And many causes were triggering other events that eventually made things worse and worse and worse and caused an amplifying feedback cycle, or circulus vitiosus as we call it, which then eventually made the situation uncontrollable. But in principle, the error chain could have been interrupted. What are indications of criticality? What are proper actions or can be done in order to stop the domino effect and the circulus vitiosus? And in the meantime, we also have gone so far to use virtual reality simulations and experiments in order to look into alternative scenarios, how else you could actually manage the crowd in that particular situation. And it turns out that, in fact, most likely the crowd disaster would have been avoidable, even though that was a pretty, I would say, not very suited area for this kind of festival and its size in the first place. And so the question is how to avoid these kind of disasters in the future. And here is where new technology comes in. So in many cases, of course, people are having the smartphone with them, and there are now apps which would basically evaluate the densities and speeds of flow and criticality of the area, and basically indicate where there's a high density and where there's a potential problem. And not only this, they would also basically give indications to people. So this is for the case of the Lord Mayor show in London. Somebody is trying to find his way. And here you see density profiles. And eventually, you know, it would, there's a control room that basically has an overview of the situation. And the person would be informed about the congestion and that it would be better actually to use another route to get to that festival, right? All of that in a way that protects the privacy of the individual user. So here only aggregate quantities are available to the police. Here again, some take-home messages. I think the most important point is that if many people interact, then there will be emergent pattern formation phenomena, self-organization phenomena such as lane formation, oscillatory flows, stripe formation, all of this. And that has implications for efficient designs of pedestrian facilities. It also has very important implications for the safe management of mass events. And so we can say that this kind of physics-inspired approach has led to deeper insights into the collective dynamics of people and how it can be managed in a safe way, considering the phenomenon of self-organization and using it favorably.